Hello, my dear wonderful genius students. I welcome all of you to my YouTube channel. This is lecture number 27 on complex analysis, and from today onwards, I am going to start the contents of module number 4. First, let me talk about what are the topics that I'll be covering. First, I will define what is a singular point or singularity of a complex function. Next one is types of singularity. The third topic will be a brief discussion on the principal part of Lorentz series. Finally, I will solve some numerical problems to check the nature of singularity. Now, let me define what is a singular point or singularity of a complex function. Students, singular point basically means it is the point at which the function f of z is not analytic. For example, we have a function f of z which is equal to 1 by z minus 2. Here we have seen that if we put z equal to 2 here, then this function becomes infinite. So we can say that z equal to 2 is the singular point of the function f of z. Next, types of singularity. Students, broadly, singularity is classified into two categories. First one is isolated singularity and second one is non-isolated singularity. Again, this isolated singularity is further classified into three categories. First one is removable isolated singularity, second one is pole, and third one is essential isolated singularity. In this video, I will give detailed explanation on isolated singularity only, and in next video I will give detailed explanation on non-isolated singularity. Okay? Next, I am going to define what is isolated singular point or isolated singularity. First, let me read the definition. A singular point z equal to a is said to be isolated singular point if there exist no other singular points in the neighborhood of z equal to a. Now, let us understand this definition through one example. Suppose z equal to 2 is a singular point. We assume that there is no other singular point in the neighborhood of z equal to 2. Then under this condition, the point z equal to 2 is said to be isolated singular point. গতিকে বুজি পোৱা গ'ল নে isolated singular point কি হয়? So ইয়াত আমি কি কনসিডাৰ কৰিছো z equal to 2 এটা singular point আৰু লগতে কৈছো কি ইয়াৰ চাৰিওকাষে কোনো বেলেগ singular point নাই। যদিহে এই কন্ডিশনটো স্যাটিসফাই কৰি থাকে তেতিয়া আমি কম z equal to 2 is a isolated singular point। ঠিক আছে? But if there exist other singular points in the neighborhood of z equal to 2, then the point z equal to 2 is said to be non-isolated singular point. This topic will be explained in detail in my next lecture. Okay, students, for this example, z equal to 0, z equal to 1 and z equal to 2 are isolated singular points because in the neighborhood of z equal to 0, 1 and 2, there are no other singular points. Now, let us move to next topic, a brief discussion on the principal part of Lorentz series. Students, we know that according to Lorentz theorem, we can expand a function f of z about a singular point z equal to a in this way. F of z is equal to summation n goes from 0 to infinity a n into z minus a whole to the power n plus summation n goes from 1 to infinity b n divided by z minus a whole to the power n. The part containing positive powers of z minus a is known as the analytic part, and the part containing negative powers of z minus a is known as the principal part. One important point is that the nature of singularity depends on the number of terms present in the principal part of the Lorentz series. If this principal part contains infinite number of terms, then we get essential isolated singularity. Again, if this principal part contains finite number of terms, then we get poles. Finally, if the principal part does not have any term, then we get removable isolated singularity. Now, let me define removable isolated singularity, pole and essential isolated singularity separately. First, what is removable isolated singularity? Students, the point z equal to a is said to be removable isolated singular point if it satisfies any one of these two conditions. First condition is that there should be no term in the principal part of the Lorentz series, or limit z tends to a f of z exists and the limiting value is finite. Next one is pole. The point z equal to a is said to be a pole if there is finite number of terms in the principal part of the Lorentz series, or limit z tends to a f of z exists and this limiting value is infinite. Next topic is order of a pole. The highest negative power of z minus a is called the order of the pole z equal to a. Again, if there is infinite number of terms present in the principal part of the Lorentz series, or limit z tends to a f of z does not exist, then the point z equal to a is said to be essential isolated singular point. Okay? Finally, let us solve some numerical problems to understand the theory part. The problem says we have to comment on the nature of singularity at z equal to 0 if number 1 f of z is equal to sin z divided by z, number 2 f of z is equal to sin z divided by z square, number 3 f of z is equal to sin 1 by z. Now, let us solve problem number 1a. So, given f of z is equal to sin z divided by z. Here we have seen that z equal to 0 is an isolated singular point. Here z equal to 0 is an isolated singular point. Now, we have to comment whether it is removable isolated singular point or pole or essential isolated singular point. Now, f of z is equal to sin z divided by z. Now, let us expand sin z term. So, finally, we will get z minus z cube divided by 3 factorial plus z to the power 5 by 5 factorial minus dot dot dot. Next, let us multiply this term with this term. So, finally, we will get 1 minus z square divided by 3 factorial plus z to the power 4 by 5 factorial minus dot dot dot. Here, we have seen that there is no principal part present in f of z. So, therefore, we can say that z equal to 0 is a removable isolated singular point. Now, let me write these points. Since there is no term present in the principal part of f of z, so z equal to 0 is a removable isolated singular point. Now, let us apply second condition to check the nature of singularity. Alternative method. Given f of z is equal to sin z divided by z. Here z equal to 0 is an isolated singular point. Now, limit z tends to 0, f of z is equal to limit z tends to 0 sin z divided by z. We know limit z tends to 0 sin z divided by z is always 1, which is a finite quantity. Since limit z tends to 0 f of z is a finite quantity, so we can say that z equal to 0 is a removable isolated singular point. Now, let me write these points. Since limit z tends to 0 f of z is a finite quantity, so z equal to 0 is a removable singular point. Next, let us solve problem number 2. According to problem number 2, f of z is equal to sin z divided by z square. Here we have seen that z equal to 0 is an isolated singular point. Now our target is we have to check whether it is removable isolated singular point, pole, or essential isolated singular point. For that we have to expand the term sin z. So after expanding this term sin z, we will get z minus z cube divided by 3 factorial plus z to the power 5 by 5 factorial minus dot dot dot. If we multiply this term with this term, we will get 1 by z minus z divided by 3 factorial plus z cube divided by 5 factorial minus dot dot dot. Here we have seen that there is one term in the principal part of f of z. So therefore z equal to 0 is a pole of order 1 because here highest negative power of z is 1. Okay? Let me write these points. Since there is one term finite, since there is one term present in the principal part, of f of z, so z equal to 0 is a pole of order 1. Now let us apply second method. So given f of z equal to sin z divided by z square, so z equal to 0 is an isolated singular point. Now limit z tends to 0, f of z is equal to limit z tends to 0 sin z divided by z square. Now apply product law for limits. So we can write limit z tends to 0 1 by z into limit z tends to 0 sin z divided by z. We know the value of this term is 1 and the value of this term is infinity. So infinity into 1. So finally we have seen that the limiting value of f of z is infinite. So therefore z equal to 0 is a pole. Since limit z tends to 0, f of z is infinite, so z equal to 0 is a pole. Finally, let me solve problem number 3. According to problem number 3, f of z is equal to sin 1 by z. Again, we have seen that z equal to 0 is an isolated singular point. Now, our target is we have to check whether it is removable isolated singular point, pole, or essential isolated singular point. So for that we have to expand this term sin 1 by z. Now f of z is equal to sin 1 by z. So this term can be written as 1 by z minus 1 by 3 factorial into 1 by z cube plus 1 by 5 factorial into 1 by z to the power 5 minus dot dot dot. Here we have seen that there is infinite number of terms in the principal part of f of z. So therefore z equal to 0 is an essential isolated singular point. Since there is infinite number of terms present in the principal part of f of z, so z equal to 0 is an essential isolated singular point. This is all about today's video, and I hope that you have learned a lot from this video. In my next video, I will give detailed explanation on non-isolated singularity. Okay?